If you want to write these linear transformations in matrix form, you're going to need to know how that transformation acts on a basis for V. And again, I'm talking in general terms about a transformation that maps V onto W, so I'm going to need to know how that transformation acts on a basis for V. Now, you can start with the standard bases, or sometimes you'll have to start with non-standard bases depending on the situation. Let's try one just to sort of explain where I'm going with this. Suppose I've got a transformation that maps xy onto 2x minus 3y, x minus y, y minus 4x. All right, so you can see that I'm going from R2 to R3. What are the coefficients of my x's? The coefficients of my x's are 2, 1, negative 4. The coefficient of the y values, y coordinates, are negative 3, negative 1, 1. Which means that I can write it like this. I can say that if I do a transformation on the first basis vector in the standard ordered basis for R2, I will produce 2, 1, negative 4. And if I perform the transformation on the second vector in the standard ordered basis for R2, I'll produce negative 3, negative 1, 1. So now I'm going to take those two columns and I'm going to arrange them into a matrix for the transformation. The standard matrix for the transformation is this 3-row, 2-column vector. 2, 1, negative 4, negative 3, negative 1, 1. All right, so you can take whatever you want to transform and multiply it by A, and you'll get an answer out under that transformation. Okay, so that's the sort of simple version when you're dealing with something operating under the standard ordered bases. You're doing a transformation of the basis vectors in V, and it produces new elements. Okay, in this case, we input values in R2, we got out values in R3. That's the transformation. All right, let's try another one. This time I want to find the image of this vector, 3, negative 1, under this transformation. A transformation that maps xy onto x plus y, x minus y, 2x, 2y. Now, if you were boring, you would probably just take that 3, negative 1 and say, all right, I'm going to put a 3 in for x, I'm going to put a negative 1 in for y, and I'm going to get out 4 numbers. But you would be boring, and we don't want to be boring. So, because we're dealing with standard bases here, I can actually set up my transformation matrix right away. My transformation matrix, the first column are going to be the x values. So the first one has an x value of 1, second one has an x coefficient of 1, the third one has an x coefficient of 2, the fourth one does not have an x, so we put in a 0. In the second column, coefficient of y is 1, is negative 1, third coordinate is 0, fourth coordinate is 2. So that is my transformation matrix. Now I'd like to take the transformation matrix times my vector v. So I get 1, 1, 1, negative 1, 2, 0, 0, 2, and multiply that by 3, negative 1. Now what do I expect to get out of this? My matrix A has 4 rows and 2 columns. Matrix V has 2 rows and 1 column. I'm expecting to get out a matrix that's 4 by 1. So 4 rows, 1 column. All right, so 1 times 3 is 3. 1 times negative 1 is negative 1. 3 minus 1 is 2. Okay, second row. 3 plus 1 is 4. Third row, 6 plus 0 is 6. Fourth row, 0 plus a negative 2 is negative 2. And if you want, you can verify that this matrix here is the same thing you would have gotten had you taken that 3, negative 1 and thrown it into that transformation right there. So I want to do one that was easy enough for you to check. What if we want to apply compositions of linear transformations? It's not a new idea to you because I promise you've done compositions of linear compositions before. I mean, not in English class, not those compositions. Compositions of linear transformations. Let's go back to high school algebra. When did you do this? Maybe in the 9th grade, 8th grade, 7th grade. You had such a thing as f of g of x. That's a composition. You started with a domain over here, and first you applied the inside function. So you applied some function, g, and you ended up with a g of x. Then you took the result of that, and you applied f of x, because you always work from the inside out. And when you got done, you had something here that was f of g of x, right? So if you had, let's say, f of x was x plus 2, and g of x was x squared, if you wanted to do f of g of x, you would do the x squared part first, and then take that answer and add 2. So apply the g function, take the result of that, apply the f function. In here goes your result of f of g of x. All right, how does this work with linear transformations? Well, very similarly. Suppose you started here with t sub 1 that maps Rn onto Rm. And then you have a transformation 2 that maps Rm onto Rp. Right? So n dimensions, m dimensions. The way I'm setting this up, I'm taking the answer from the first transformation and throwing it into the second transformation. Notice the way I did it? It has to work that way, because otherwise I can't match up the dimensions. So what comes out of the first transformation must fit into the second transformation. So suppose I've got some vector space V over here, and this operates in Rn, right, n-dimensional vector space. And over here is all of Rm. So I take vectors here, right, in this group here, and I map them through a transformation. I'll call the first transformation t sub 1. And I come out with elements in here, which are elements in the range. So the range is a subset of all of Rm. So over here now, we're in m-dimensional space. Now, I've got another transformation I'd like to apply, t sub 2. That's going to land me here in p-dimensional vector space, but in there is the range of that transformation. So the range, again, is a subset of all of Rp. So I apply the first transformation, then I apply the second transformation. I can write this two ways. All right, let's slide this up just a little bit so that we can write this two ways. I can write this as t equals t sub 2 composite t sub 1, right? That little circle there is not a time sign. That circle is the composite symbol. So t sub 2 composite t sub 1. How did we work this? We worked it from the inside out, just like we did with that f of g of x. I applied the transformation on the inside first. Then I applied the transformation on the outside. You could also write this as the transformation of vector v equals t sub 2 of t sub 1 of v. And now, by those same algebraic composition rules, you can see that you would apply the inside transformation first and then the outside transformation. So you would do t sub 1 first and then t sub 2. Well, let's assign each of these a standard matrix. Let's let A sub 1 be the standard matrix for the first transformation for t sub 1, and we'll let A2 be the standard matrix for the second transformation. Then the standard matrix for the composite, right? Remember, T is the composite. For the standard matrix for T is a new matrix A that is A2 times A1 in that order. So if you're going to do transformations that are composites, T sub 2 composite T sub 1 means you do the transformation T1 first and then T2. But when you multiply the transformation matrices, you actually multiply them in that order, T1 or T2 T1, or in this case A2 A1. And yes, it does make a difference because, right, go back to my idea with the x plus 2's and the x squares. It matters whether you square it first and then add 2, or add 2 first and then square it. So the same thing's going to happen here. You want to do A2 A1, that's the transformation of T sub 2 composite T sub 1. All right, let's try one or two or a few. Suppose I've got these two transformations. The first transformation in xy maps it to 2x, negative 3y, x plus y. So the first transformation maps elements in R2 onto elements in R3. The second transformation takes elements in R3 and maps them back to R2 in this way. So T sub 2 maps elements in R3 onto R2. I would like to find T sub 2 composite T sub 1. All right. Well, let's first set up the individual matrices. Matrix A sub 1 is going to go with the first transformation. So it's going to take elements in R2, map them up into elements of R3. So this one's going to have 3 rows and 2 columns. Would make sense then that the first column are my x's, the second column are my y's. So I'm going to have a 2, I'm going to have a 0, and then a 1, right? Because there's 2 x's here, there's no x's here, there's 1 x there. The y's are going to have none in the first group, negative 3 in the second group, 1 in the third. Okay. How about A sub 2? A sub 2 is going to be the reverse. It's going to have 3 columns and 2 rows. And that's going to be a little bit longer. This time I have x's, y's, and z's. First one has 1x. The second one doesn't have any x's. Then I've got negative 1 for a y, positive 1 for a y. The third one has no z's in the first element and 1 z in the second element. All right, so there's my A2. Specifically, if I want the transformation that is T sub 2 composite T sub 1, I need to multiply them in the opposite order of the way I have them written here. So the transformation matrix A is A2, A1. So it's 1, negative 1, 0, 0, 1, 1. What is this? This is a 2 by 3 matrix. And then A1 is 2, 0, 0, negative 3, 1, 1. 3 rows and 2 columns. So matrix A is going to be a 2 by 2 matrix. 2 plus 0 is 2. 0 plus 3 is 3. All right, then if I come down here, I get 0 plus 0 plus 1. I get 0 minus 3 plus 1 minus 2. All right, that's my transformation matrix. What if I want to find the transformation T sub 2 composite T sub 1 for the vector 2, 4? All right. Well, then take that transformation matrix that you have for the composite and multiply it by 2, 4. It would make sense that we're going to get an answer in R2. 2 times 2 is 4. 4 plus 12 is 16. Then I've got 2 minus 8, which is negative 6. Okay. So there's my answer, 16, negative 6. Now, the next question that comes out of this composite is, can I go backwards? Is there ever a way to turn back? Well, there is. If matrix A has an inverse. Does it always? Well, let's find out. Matrix A, that transformation matrix, was given as 2, 3, 1, negative 2. Let's try to find A inverse. First thing is, what is the determinant of A? The determinant of A is negative 4 minus 3, right? Negative 4 minus 3, determinant of A is negative 7. All right, so A has an inverse. What is that inverse? That inverse is negative 1 over 7 times, and then I switch the 2 going down this column, or this diagonal, and I negate the other 2. All right, so this gives me the matrix positive 2 sevenths, positive 3 sevenths, positive 1 seventh, negative 2 sevenths. Now, if this really works, I should be able to take that inverse over there, multiply it by what I got, and I should end up with the original vector. So multiplying by the inverse should take me back to the original vector. Let's see if that works. Let's take A inverse times the vector. So 2 sevenths, 3 sevenths, 1 seventh, negative 2 sevenths, and multiply that by 16, negative 6. All right, what does that give me? I'm going to write it out in long form here. 2 times 16 is 32. 3 times negative 6 is negative 18. And that's over 7. And then the bottom one is going to be 16 plus 12 over 7. So 32 minus 18 is 14. 14 over 7 is 2. And on the bottom, 28 over 7 is 4. So I just went back and I got the original value from that transformation by taking the inverse. So it turns out that this is leading us to an equivalence theorem. Assuming that I have some standard matrix A that maps on a linear transformation from Rn to Rn, so we're talking about a transformation that goes from one dimension to the same dimension space, then there's 3 things that come out to be true. The first thing is that the transformation is invertible, meaning I can go backwards and get that original vector by performing some inverse operation that will take me back there. The second thing is that T is an isomorphism. Right? Isomorphic meaning one-to-one and onto. So if I can take some transformation and undo the process, then automatically it's an isomorphism. And then the third thing is that matrix A is invertible. And not only is A invertible, but the standard matrix for T inverse is A inverse. So these things are equivalence statements. And then the other thing that comes out of this is if A is invertible, A inverse is the standard matrix for T inverse. So if you can undo the process, then the inverse of matrix A will get you the inverse of the transformation. It will undo what you just did. All right, let's take a look at another example. Suppose I've got this transformation. I got a transformation that maps x, y's onto x plus y, x minus y. All right, so not the most fascinating transformation in the world, but let's give it a try. The standard matrix for the transformation is going to be 1, 1, those are my x's. 1, negative 1, those are my y's. All right, this is the standard matrix for the transformation. Suppose I want to find the transformation on the vector 2, negative 6. Then I would take 1, 1, 1, negative 1, and multiply it by 2, negative 6. Right, what do I get? 2 minus 6 is negative 4. 2 plus 6 is 8. Right, so there's my answer, negative 4, 8. Then what's the inverse? Well, first of all, we got to find out if A has an inverse. Take the determinant of matrix A. 1 times negative 1 is negative 1 minus 1, so negative 2. All right, yes. It's got a determinant that's not equal to 0. It must be invertible. All right, so A inverse is negative 1/2, and then I multiply by the matrix that I transform. So I switch it around. I put the negative 1 up here, the 1 down here, and I negate both of the other two. So A inverse is 1/2, 1/2, 1/2, negative 1/2. I could perform the inverse operation now using that matrix. So the inverse transformation applied to negative 4, 8, which is what I got when I did the first round, is going to be that new inverse transformation matrix, 1/2, 1/2, 1/2, negative 1/2, times the matrix negative 4, 8. What do I get? I get negative 4/2 plus 8/2. That's the top entry. The bottom entry is negative 4/2 minus 8/2. So on the top, 8 minus 4 is 4. Half of 4 is 2. On the bottom, that gives me a negative 12 on the top. Half of negative 12 is negative 6. The other thing I can do is I can look at that inverse matrix to figure out what my formula is. So if you want a formula, you can get a formula. T inverse of x and y is, now remember these are the x's and those are the y's, so the first entry will be 1/2 x plus 1/2 y. That's the first row across. The second row across is 1/2 x minus 1/2 y. So there is the formula for my transformation. All right, I think I got two other little quick things to take a look at. One of them is you can apply these transformations to angle measures. Right? I've been applying them strictly to things that are in terms of x's and y's. But suppose I want to take a transformation that is the counterclockwise 120-degree revolution. And I want to find the transformation of a vector where the vector is the vector 2, 2. Well, remember how we set these things up? There's a standard matrix that works for these angle rotations. We start with cosine theta, sine theta in the first column, and then it becomes negative sine theta, cosine theta in the second column. So if I apply it to a 120-degree revolution, that'll give me the cosine of 120 degrees. So the cosine of 120 degrees, well, all right, 2 pi over 3 radians, negative 1/2. Negative sine of 120 will give me negative root 3 over 2. Then the sine of 120 will just give me the positive version, positive root 3 over 2, and again a negative 1/2 down here. So if we want the transformation of that vector, we should just take negative 1/2, negative root 3 over 2, positive root 3 over 2, negative 1/2, and multiply it by the vector 2, 2. And we'll find out what happens to that vector under that transformation. We'll end up with a negative 1 minus the square root of 3, and then on the bottom, a square root of 3 minus 1. And that will be the vector that results from rotating counterclockwise that vector 2, 2 by 120 degrees. Let's take a look at one other thing, and that is non-standard bases. I don't want to go too deep into this, but I do want to at least give you an example of what it looks like. So suppose I have some operation, I'm going to call it d sub x, and that maps elements in p sub 2 onto p sub 1. Specifically what it does is it maps the derivative of a polynomial with degree 2 or less onto a polynomial of degree 1 or less. So that means that my standard basis right now is going to be 1x x squared. But the new basis is not 1x x squared, right? If I'm mapping it onto P1, my new basis is just 1 and x. So I need to find each transformation for the original basis using this polynomial. So I want to find t of v using p equals a sub 0 plus a sub 1x plus a sub 2x squared. When I do this, my goal is to apply the operator to the elements in basis B and answer in terms of B prime. Okay, so I'm going to apply that derivative operator to the elements in basis B and answer in terms of B prime. So let's start with this first element here, 1. Apply that operator to 1, and I get 0, right? The derivative of 1 is 0. How does that match up to B prime? Well, it's no 1s and no x's. I'm going to put a 0, 0 over here. So no 1s, no x's. Right? Apply that derivative operator to x. That's the second element in basis B. What does that give me? That just gives me 1. In other words, it gives me 1, 1, and no x's. 1, 1, and no x's. Right? Apply that derivative operator to x squared. The derivative of x squared is 2x. So what does that give me? It gives me no 1s and 2x's. So I'm going to put 0, 2 over here. Take those 3 columns and assemble them into a matrix. So these 3 columns over here will become the standard matrix for the transformation. It'll be 0, 0, 1, 0, 0, 2. Now, let's multiply that by the 3 coefficients. So let's take that matrix times a sub 0, a sub 1, a sub 2. What do I get? I get 0 plus a sub 1 plus 0, and then I get 0 plus 0 plus 2 a sub 2. What is this? This is a new polynomial. That is a sub 1 plus 2a sub 2 times x. So you could think of it as a sub 1 times 1 plus 2a sub 2 times x. Is it true that this here is the derivative of a sub 0 plus a sub 1x plus a sub 2x squared? Sure it is. And that matrix actually lets us calculate the derivative of that polynomial by setting up a matrix that's relative to a different basis. In other words, is not the standard ordered bases, it's a new basis. So the original one contained 1x and x squared. The new basis contained 1 and x. We did a transformation that included the old and the new, and we came up with a matrix that will let us essentially take the derivative of a function. Pretty neat.